All right, section 6.6, we are going to talk about surfaces and computing surface integrals. And so you can kind of think of this as an extension of those line integrals, just a higher dimension version of that. All right, so before we can talk about computing surface area and surface integrals, I need to talk about surfaces in space in a little bit more detail. So just as a quick review, on the top of the screen, I have jotted down how we write a plane curve or a space curve in parametric form. So plane curve is just in 2 dimensions, space curve is in 3 dimensions. Regardless, we need only one parameter, and we can describe its position, its x, y, and z, using our parameter t. When we're talking about a surface as opposed to just a curve or a line, we are going to need to use 2 parameters. Okay, so if we want to write a surface would be something like a plane. That's an example of a surface. So if we want to write a plane in parametric form, we're going to have to use 2 parameters. You can use any letters you want. I'm going to use the letters U and V. So the first thing I want to do is just get a little bit comfortable with these surfaces in parametric form and think about how can we identify and sketch the surfaces given. So I have the following surface, R equals VI plus cosine uj plus sine uk, and then I just added some limits to those parameters. We're only going to consider this when u is between 0 and 2 pi, and v is between 0 and 3. So this surface is written in parametric form. It's also written in vector form. So the x is given by the parameter v. So the x values always go from 0 to 3. The y values are given by the parametric equation cosine u, and the z values are given by that parametric equation sine of u. And we're going to let the u's go from 0 to 2 pi. So a nice way to visualize this is to try to eliminate the parameter. There's 2 parameters, so we're going to have to do a little bit of thinking, a little bit of manipulation to eliminate the parameter. And I noticed that both the y and the z have u's in them. And we've got a sine and a cosine. So that Pythagorean identity says cosine squared plus sine squared is 1, which in terms of y and z would be y squared plus z squared equals 1. So the y and the z parametric equations are describing a cylinder. And then the x equation has a different parameter, this parameter v. And so that means the x's are just going to vary from 0 to 3. So what we have is we have a cylinder. So it looks like that circle in the YZ plane. And then along the x direction, the x values just vary from 0 to 3. So we have a cylinder that runs from x equals 0 to x equals 3. Here's another one. Let's see if we can identify and sketch the surface given by the following parametric equations. So our x is 3 cosine v cosine u. Y is 3 cosine v sine u, and z is sine of v. So I'm going to see if I can eliminate the parameter again, and I'm going to take advantage of some Pythagorean identities because I have sines and cosines. And so I'm going to start, because only the x's and y's have u's in them. So I'm going to deal with that. And so I notice if I do x squared plus y squared, so I'm just going to take those parametric equations and square them. So x squared is 9 cosine squared v cosine squared u. And the y squared is 9 cosine squared v sine squared u. So I just squared the x and the y. And then I can see that both of those terms have a 9 cosine squared v So that's my GCF. I'm going to pull that out front. And I'm left with a cosine squared plus sine squared, which just turns into a 1. So this simplifies all the way down to 9 cosine squared v. So x squared plus y squared simplifies down to 9 cosine squared v. And then let's see if we can somehow combine this with the z equals sine of v. Again, thinking about that Pythagorean identity. I know sine squared v plus cosine squared v has to equal 1. Sine squared v would be z squared. Let's see, we just figured out x squared plus y squared is 9 cosine squared v. So if we divide everything by 9, cosine squared should be x squared divided by 9 plus y squared divided by 9. And so I have successfully eliminated the parameter here. We are talking about the following surface, z squared plus x squared over 9 plus y squared over 9 equals 1. And this is an ellipsoid. So it goes up to z equals 1. And then on the x and the y axes, it should go out to 3. So I have a surface that is an ellipsoid. All right, what if we want to work in the opposite direction? What if I want to come up with a parameterization of the surface? So I'm giving you the surface now. Let's work in the opposite direction. So can we come up with parametric equations for the surface z equals the square root of x squared plus y squared? So because this surface happens to be solved for z, one kind of simple option is you can just let x equal u and y equal v, and then z would be the square root of u squared plus v squared. Now, there is a restriction here. They're telling us z is only between 0 and 1. So that means this square root of u squared plus v squared has to be between 0 and 1. So that puts some kind of restriction or bounds on our parameters. We could square all the sides and say that means u squared plus v squared has to be between 0 and 1. So again, those are some bounds on our parameters. Now, when you're dealing with something that, like in this case, we're talking actually about a cone, something that's kind of circular, it's often easier to think about this kind of like in polar coordinates. But what I mean by that is to try to use some sines and cosines in your parameters. The advantage of that is it's going to make it a little bit easier to put restrictions on those parameters. So this restriction that u squared plus v squared is between 0 and 1 could potentially be hard to work with later on when we're trying to set up an integral. All right, so the other option I have is I could let x equal v cosine u and y equal v sine u. This is very similar or analogous to our polar coordinates where we would say x equals r cosine theta, y equals r sine theta. I'm just using u's and v's just to be consistent, but I guess I could use r's and thetas instead. So this is a good starting point if you have something kind of circular and you're trying to think about it with sines and cosines. So then the z would be the square root of x squared plus y squared, so the square root of v squared cosine squared plus v squared sine squared. We can factor out a v squared. We're left with square root of v squared, and I'm going to say that just equals v. Since my z's are always positive, I don't have to worry about negatives in there. So there's my parametric equations. X is v cosine u, y is v sine u, and then we'll say z is v. The advantage of this particular format is then I can take care of this z equals 0 to, or z goes from 0 to 1 a little bit more simply. We can say that since z is v, my v values, it's it's a mouthful, have to be between 0 and 1. And since u is describing an angle, we could say we go all the way around the circle from 0 to 2 pi. So I can put the following restrictions. V is from 0 to 1, u is from 0 to 2 pi on my parameters, and now I'm talking about that exact piece of the surface that I'm interested in. All right, let's do one more. Parameterization of the plane, 2x minus 4y plus z equals 4. So I'm going to start by just letting x equal u, y equals v, and then I could just plug that into the equation and solve for z. So if x is u, 2u minus 4v plus z equals 4. Solve for z. Z is 4 minus 2u plus 4v. And those are my parametric equations. I can write it in vector form. In this case, we're talking about the entire plane, so I don't have to put any kind of bounds or restrictions on my parameters because we're not limiting ourselves to a portion of the plane. U and v can be anything because we're talking about this entire plane. All right, so that is a quick kind of overview of our surfaces in parametric form. One more thing I need to mention before we can get to the integrals is when we're talking about surfaces in parametric form, we can define normal vectors to these surfaces. So I've got some kind of, surface in space. My normal vector is going to be orthogonal or perpendicular to a tangent plane at that point. So to find the normal vector, you can find partial derivative of your surface with respect to u, partial derivative of your surface with respect to v, and then if you take the cross product of Ru and Rv, you will get a vector that is normal to the surface. That vector might point up or down, and I'll mention a little bit more about that in a minute. So we might talk about surfaces that are oriented upward or downward. We're just talking about whether our normal vector that we computed points up or down. All right. So finally, this is our main goal of this section. Let's talk about finding surface integrals. And so we're going to start by talking about how do we find surface area. So how do we find surface area when we're given a surface in parametric form? We can actually integrate the magnitude of that Ru cross Rv, and we can integrate it over the area made by that surface in the UV plane. Let me show you an example of this. I'm not going to actually derive this for you. Your textbook has a lot of derivations in it if you're interested, or I could chat with anyone outside of class if they're interested. But basically, if we want to find surface area, we're going to integrate the magnitude of our Ru cross Rv, and we're going to integrate that basically over the projection of that surface in the UV plane. Okay, so what does that mean? Let's see if we can use this definition to find the surface area of the cone given by the following parametric equations. X is u cosine v, y is u sine v, and z is u. The u's go from 0 to 2, and the v's go from 0 to 2 pi. So I'm going to start by computing r sub u. So what I'm doing here is I'm just taking the derivative with respect to u of these components. So derivative of x with respect to u is just cosine v. Derivative of the y component with respect to u is sine v. Derivative of the z component with respect to u is 1. And then I'm going to find my derivatives with respect to v. So derivative of my x component is negative u sine v. Y component, u cosine v. Z component is just 0. Next step, I'm going to compute the cross product of RU and RV. So I put those derivatives into this kind of matrix so I can, or determinant, I guess you could say, so I can compute that cross product. So I component would be 0 minus u cosine v. J component 0 minus a minus, so plus u sine v. Of course, we have that negative right there. And then K component u cosine squared v plus u sine squared v. And that simplifies down to u. So that just simplifies down to u. This vector that I just computed is actually normal to this surface. The vector I computed is normal to this surface. And so now, to find my surface area, I'm going to find the magnitude of this vector, and then I'm going to integrate that over these bounds of u and v that were given. All right, so magnitude of this RU cross RV, let's see, we get u squared cosine squared, and then y component squared would be u squared sine squared. I dropped the negatives because I'm squaring them. And then z component squared is just u squared. I can simplify that by factoring a u squared out of the first two terms. And I'm left with that cosine squared plus sine squared, which is 1. So we are left with the square root of u squared plus u squared. That's square root of 2u squared. We could also write this as root 2 times u. Again, those u's are positive, so we can just simplify that right away. So to find my surface area, I'm going to integrate square root of 2u with respect to u and v. And the u values go from 0 to 2. And then the v values go from 0 to 2 pi. So inside integral, I get root 2 u squared over 2. Plug in the bounds of integration. That should be 2 root 2. Integrate that answer with respect to v, plug in the bounds of integration. I got 2 root 2 times 2 pi. So that's 4 pi root 2, and that is the surface area of the cone that was given to us. All right, what I really want to focus on, though, I feel like I've said that a lot, finally, let's talk about surface integrals. So we're going to talk about computing surface integrals. So basically, the first type of integral we're going to talk about is we have a function. We can have a function of 3 variables, and we are now integrating it over a surface. We're going to talk about 2 different ways we can do this problem. The first way is we are going to change this ds into the quantity square root of 1 plus g sub x, so that's derivative of g with respect to x, squared, plus g sub y squared dA. Where g is the surface that we're integrating over. So g is the surface that we're integrating over. So this is the first method we're going to use to compute surface integrals. This is really similar to, let's see, arc length. So there is an arc length formula where you have like a square root of 1 plus y prime squared. So it kind of reminds me of that, similar to that type of formula. All right, so how does this work? Let's see if we can compute the integral of x squared plus yz for the first octant portion of the plane. X plus y plus 2z equals 4. So the surface that we're given, I'm going to go ahead and take that and solve it for z. the surface that we're given is our plane. So that is z equals 2 minus 1/2 x minus 1/2 y. So that's what we're calling g. That's the surface we're integrating over. So the ds in this integral is going to turn into the square root of 1 plus g sub x squared plus g sub y squared, and those are my partial derivatives. And then dA, where the dA, the area we're integrating over, is the projection of that surface on the xy plane. So g sub x is negative 1/2. Derivative with respect to y is also negative 1/2. Plug that in. So my ds here is going to be the square root of 1 plus 1/4 plus 1/4. I got square root of 3/2 dA. So in this integral, I can replace the ds, which is technically a little tiny, teeny piece of the surface, with root 3 over 2 times dA, where dA is just a tiny piece of the area of the projection of that surface on the xy plane. So that's kind of what we're doing in our integral, is we're converting this little differential surface into a little differential chunk of area. Again, that area that we're talking about now, the dA, is the projection of our surface in the xy plane. So in that xy plane, z equals 0. So if I plug in 0 for z, I'm just left with the line x plus y equals 4. And then if we're in the first octant, our x's and y's are positive. So we are talking about this little triangular region I have drawn on the screen in blue. So that's the area we're going to be integrating over. So the integral we're going to try to find is, we are going to be integrating x squared plus y, and then I took my surface and I plugged that in for the z. So x squared plus y times 2 minus 1/2 x minus 1/2 y. And then again, the ds is now root 3 over 2 dA. All right, so there's the integral we're going to try to find. dA is the region on the screen. So if I want to do, maybe we'll do the dy first and then the dx, come up with some bounds of integration. Before I do that, I did do a little bit of algebra. I took this constant, this square root of 3/2, and just moved it out front. And then let's see, what else did I do? I distributed the y. So I distributed the y to those parentheses. All right, if we're going to do the dy first, our y values start at 0 and stop at this line, which is y equals 4 minus x. The x values start at 0 and stop at 4. So 0 to 4. So this is the integral we need to compute. So I found the antiderivative with respect to y. I got an x squared y plus 2y squared over 2 minus, let's see, that's going to be a 1/4 xy squared and then minus 1/6 y to the third. And then I'm going to go ahead and plug in my bounds of integration. So I'm going to plug in that 4 minus x in for all the y's. Plug in 0, we get 0. And then you are going to have to do some algebra. You're going to have to expand this. You really have to expand or multiply out all of these that I've circled. You could leave the last term as a minus 1/6, 4 minus x to the third, and then use a u substitution to integrate that. I personally decided, you know what, I'm just going to do tons of algebra. There it is. Tons of algebra to expand this. I don't think I'm going to talk through this. It's just lots of foiling, combining like terms, really messy. Feel free to pause it if you want to see what I did. But basically, I just multiplied everything out, combined like terms, and then I circled in blue what I got for my final answer there. So lots of just kind of ugly algebra. So finally, I just copied that answer down. So finally, I'm going to have to integrate that answer, which was the negative 13/12 x to the third plus 5x squared minus 4x plus 16/3. I'm going to integrate that with respect to x. And I shouldn't forget about that constant that's out front. So I've got that square root of 3/2 in front. So found my antiderivative, plugged my bounds of integration, and then I used a calculator when I plugged the 4 in. I got 80/3 times square root of 3/2. I'm going to just leave my answer like that. All right, so there's my surface integral. So I've integrated a function over a surface in space. Let's do another one. It's kind of a long process. Let's get a second example in. So I want to integrate the following function over the surface z equals the square root of x squared plus y squared, where z is less than or equal to 9. So my surface is already solved for z, square root of x squared plus y squared. I'm going to go ahead and find the derivative of that with respect to x and with respect to y. And so I did some of that in my head. I had to use the chain rule. I guess I can write it out. I got 1/2 square roots. And then using the chain rule, I had to multiply by the derivative of the inside, which was 2x. Cancel the 2's out. So that's how I got that x over the square root of x squared plus y squared. Same thing to get my derivative with respect to y, except there's a y on the top now. So I found my derivatives with respect to x and y, g sub x and g sub y. And that's important because the ds in this integral is going to be the square root of 1 plus my g sub x squared plus my g sub y squared, and then dA. We can simplify this further because when you square the gx and the gy, you actually get like an x squared over x squared plus y squared over x squared plus y squared. And if you add those two terms together, which you can do because they have a common denominator, you end up with something that simplifies down to 1. 1 plus 1 is 2. So my ds is root 2 dA. So we can change this ds, talking about these little tiny pieces of the surface, to root 2 times little tiny pieces of area. And the area we're talking about is the projection of the surface in the xy plane. Okay, so I just replaced ds gets replaced with that root 2 dA. And that dA is that my projection in the xy plane. So I'm going to just sketch a quick picture of this surface. We are talking about a cone, and that cone is going from z equals 0 up to z equals 9. And so the projection that makes on the xy plane is actually the circle x squared plus y squared equals 9. 9 because that's where the cone stops. So we're going to be integrating over that circle that I've drawn, the projection in the xy plane. Okay, so just copy down my integral. Let's see, one more thing I need to do. I want my integral to only have x's and y's in it. So I'm going to replace this z squared using that surface. So if z is the square root of x squared plus y squared, z squared, if you square both sides, is x squared plus y squared. I can simplify that. I can combine like terms. And then I actually have a common factor of 2. And so I can factor out that square root of 2. So now I've got square root of 2, square root of x squared plus y squared times square root of 2. Root 2 times root 2 is just 2. And so I'm left with trying to integrate the square root of x squared plus y squared dA, where the area we're talking about is that circle of radius 3. Lots of x squareds, lots of circles in this problem. This is a great candidate for polar coordinates. So I've just copied down my integral again. I'm going to convert this into polar coordinates. I'm going to change the dA to an r dr d theta. And the square root of x squared plus y squared is actually just r. So I'm going to have to integrate r squared, and then I still have that constant of 2 in front. We're talking about a circle of radius 3, so the r's go from 0 to 3, and the thetas go from 0 to 2 pi. So we integrate r squared with respect to r. It's r cubed over 3. Plug in the bounds of integration, that's 9. Integrate 9 with respect to theta, and don't forget about that constant of 2 in front of the integral. So I ended up getting, when I plugged in my bounds of integration, I ended up getting 36 pi, and that is my final answer for this problem. So the previous 2 examples that I did involved working with our surfaces in terms of x and y. We didn't actually put anything into parametric form. In some cases, you might be given your surface in parametric form, or it just might be easier to work with it in parametric form. And in that case, our surface integral can be written, you can write your whole function in terms of your parameters, u and v, and the ds is going to turn into that magnitude of ru cross rv dA, which is essentially what we integrated to find surface area. All right, so let's do one example in parametric form. We are going to try to integrate the function x plus y over the following surface. R is 4u cosine v, 4u sine v, 3u. So we could eliminate the parameter and see if we could just work in terms of x's and y's, but because we're already given this surface in parametric form, we might as well try to work with it in parametric form. So I'm going to start by finding my r sub u. So basically, I just took that surface and I found the derivative of each component with respect to u. I got 4 cosine v, 4 sine v, 3. And then I'm going to take the derivative of each component of that surface with respect to v. And so that's how I got the negative 4u sine v, 4u cosine v, and then 0. And then I'm going to go ahead and find my cross product, ru cross rv. So let's see, I component is negative 12u cosine v. J component is going to be a negative 12u sine v. K component, 16u cosine squared plus 16u sine squared. You can factor out the 16u, use that Pythagorean identity, simplifies down to 16u. I'm going to find the magnitude of that vector. So I'm going to take the square root of the sum of the components squared. So I took each one of these components and squared them. So the first component squared, I got 144u squared cosine squared. Second component, 144u squared sine squared. And then finally that third component is the 16u. If you square that, you get 256u squared. We can simplify this down quite a bit. The first two terms, you can factor out the 144u squared, and you're left with another one of those sine squareds plus cosine squareds, so Pythagorean identities. So those first two terms just simplify down to 144u squared. 144u squared plus 256u squared is 400u squared. That becomes 20u. So this simplifies all the way down to 20u. So what does this mean? This means I can replace my ds with 20u du dv. So I'll be integrating x plus y, and the ds just turned into 20u du dv. Finally, I'm going to replace both the x and y with the parametric equations used in that surface. So I replace the x with that 4u cosine v, and then I'm going to replace the y with the 4u sine v. And we are multiplying that by that 20u. The bounds of integration are given to me through those parametric equations. The u's go from 0 to 4, and they're telling me the v's go from 0 to pi. And so there's my integral. We just have to integrate. So I'm going to distribute the 20u to both terms. And then I integrated with respect to u first. So that's how I got those u to the thirds over 3. Plug in my bounds of integration. I got 5120 over 3 cosine v plus 51 over 20 sine v. I'm going to just factor that constant out for now. And then I have to integrate the cosine v plus sine v with respect to v. So now I've got 5120 over 3 sine v minus cosine v. I'm going to plug in those bounds of integration, the 0, the pi, subtract them. And there's my final answer, 10,240 over 3. So we have two different ways we can set up these surface area intervals. We can work with them in terms of x's and y's, and we can work with them in terms of those parametric equations. So on this next screen here, I do have a little bit of a summary. So I just want to kind of point out that when we were working with line integrals back in, what was that, 6.2 maybe? We worked with our line integrals in parametric form, and notice our little ds turned into that magnitude of r prime dt. That's how we computed our line integrals in parametric form. And so it's nice to kind of see the comparison when you're doing a surface integral in parametric form. That big ds turns into a magnitude of that cross product, ru cross rv, dA. So that's kind of similar. The other thing I want to point out while I have kind of a summary of our formulas on the screen is whether we're working in parametric form or not, when we're computing a surface integral, this ds is being replaced with something dA, and that something is actually representing a magnitude of our normal vector. That's what's happening here. And we'll talk a little bit about that in our next examples. But that ru cross rv is our normal vector. And then this 1 plus gx squared plus gy squared, that's actually going to be the magnitude of the gradient of that surface g, just written in a different form. All right, so again, this is a summary of how do we find our surface integrals if we're integrating a function over a surface. Finally, last topic in this long video, what if we want to find a surface integral of a vector field? And that's exactly what we did with our line integrals, is we talked about how do we integrate a function over a path, and then we talked about, well, what about a vector field? And so that's exactly what I'm going to do here. So if I want to find the integral of a vector field, which I'm calling f, over a surface S with normal vector n, then my integral f ds, so if I integrate this vector field across this surface, technically what I'm doing here is I'm actually computing flux. I'm integrating a vector field across a surface, so I'm actually finding flux in these integrals. If I'm not working in parametric form, dot ds turns into an f dot, and then I'm going to compute this vector that's negative gx, negative gy1, where g is my surface. That vector is essentially a normal vector. Or if I'm in parametric form, my f dot ds is going to turn into f dot that ru cross rv, which is also a normal vector. Now, one thing I should mention is when we're computing these surface intervals of vector fields, we do want to orient our surface. So our surface is basically going to have a direction. And what I mean by that is we want to think about which way are we going to define our normal vector to be pointing. And so, for example, let me just try to sketch. Here's a surface. Maybe it's like some kind of paraboloid. For this particular surface, I could create normal vectors that point outward, or I could point them in the opposite direction, inward. We are going to define if our normal vectors have a positive z component, they're pointing up, and then we're going to say that the surface is oriented upward. And so that's what this formula is assuming, it's assuming that we want our surface to be oriented upward. If we wanted to orient the surface in the other direction, oriented downward, we would just change this to a positive gx, positive gy, negative 1, and that would be a normal vector that's pointing down. All right, so let's do an example. I want to compute the surface interval of f dot ds. So f is a vector field defined as x, comma y, comma z. So that's my vector field. And s is the surface z equals x squared plus y squared. So it's a paraboloid from z equals 0 to 4. And we're going to orient our paraboloid upward. So if it doesn't say assume you orient it upward, we'll do that most of the time. So I'm going to solve this problem using two different methods. I'm going to solve this problem just working in terms of x's and y's, and then I'm going to show you how we would solve it if we wanted to work in parametric form. And so many of the problems you're going to encounter, you can choose what form makes more sense to you. Sometimes one form will be easier than the other. It just kind of depends on the problem. So I'm just going to work with the x's and y's, which means I have to compute f dot this, basically a gradient vector here, this negative gx, negative gy1. So my surface is z equals, or we can call it g of xy equals x squared plus y squared. So my gx and my gy are 2x and 2y respectively. I'm going to rewrite my vector field in terms of x and y. So x component was x, y component is y, and then anywhere I see a z, I'm going to replace that with the x squared plus y squared, because that is the definition we have from our surface. So I'm replacing the z with that surface equation, x squared plus y squared. Okay, so I have my vector field written in terms of x and y. I have my gx and my gy, and so that means I have to compute f, my vector field, dotted with negative 2x, negative 2y, comma 1. That's basically a normal vector that's oriented upward. So I'm going to find my dot product. I get negative 2x squared minus 2y squared plus x squared plus y squared. I'm going to combine like terms. So I've got negative x squared minus y squared. Excuse me. So that's the quantity that I'm going to be integrating. And I'm going to be integrating that over the projection of my surface in the xy plane. So the surface we're talking about is a paraboloid. Z equals x squared plus y squared. Its shadow or projection in the xy plane is this circle, x squared plus y squared equals 4, because our z values only go up to 4. So I want to integrate this negative x squared minus y squared over that circle of radius 2, that projection in the xy plane. So I'm going to put this in polar coordinates. The negative x squared minus y squared is a negative r squared. I'm going to change the dA to an r dr d theta. We're talking about a circle of radius 2, so my bounds of integration for r go from 0 to 2. All the way around the circle is 0 to 2 pi. So I'm going to be integrating negative r to the third with respect to r. I got negative r to the fourth over 4. Plug in my bounds of integration, that's a negative 4. And then I'm going to integrate that negative 4 with respect to theta, plug in my bounds of integration, and there is my final answer, negative 8 pi. Okay, so let's just go back to the formula. So we use this top formula to do that. We took our vector field, and we dotted it with, I'm going to call that a gradient vector, this negative g sub x, negative g sub y, comma 1. Now, I want to solve this exact same problem, but I want to show you that we can do it in parametric form. So we can write parametric equations for our surface, and then we'll be dotting our vector field with our normal vector RU cross RV. All right, so skip through all this work. There we go. So now we're going to try to do this in parametric form, and fingers crossed, hopefully we get the same answer. So first thing I have to do is write this in parametric form. Because we're talking about a paraboloid, circular things, I'm going to use parameters that remind me of polar coordinates. I'm going to let x equal u cosine v, y equal u sine v. And so then z would equal x squared plus y squared. So z is going to equal u squared. The advantage of this set of parameters is now I know that my u's have to be between 0 and 2. That's because, let's see, z equals u squared, and they told me z is between 0 and 4. So if u squared is between 0 and 4, u would be between 0 and 2, and the v's would go from 0 to 2 pi. So once you have your parametric equations, then we can rewrite our vector field in terms of u and v. So my vector field was just x, y, z. So I just plugged in my parametric equation for x, y, and z. So I'm just going to plug those into that vector field. So now I have my vector field written in terms of u's and v. And then the next step is I have to find my r sub u. So I'm going to take the derivative of my parametric equations with respect to u. So dx du is cosine v, dy du is sine v, dz du is 2u. And then I'm going to take the derivative of my parametric equations with respect to v. So I got negative u sine v, u cosine v, 0. And then to get my normal vector, I'm going to do RU cross RV. So I'm going to compute cross product of those two, derivative vectors. So I component, I got negative 2u squared cosine v. J component, it becomes minus a minus a minus. So negative 2u squared sine v. And then my k component, u cosine squared plus u sine squared. We can simplify that last term down to u. You can factor the u out, Pythagorean identity. And so there's my normal vector. I do want to point out that the k component, the z component is u, which is positive. The u's are always between 0 and 2. So this vector is oriented upward. So we're talking about the surface being oriented upward. That's important if we expect to get the same answer in the previous problem. If that third component was negative, I would just multiply everything by -1 to orient it upward. All right, so finally we're going to take our vector field, which is F, and we're going to dot it with that result, that RU cross RV. So we're going to take the dot product of F and the result of our cross product. And I ended up getting -2 u to the third cosine squared minus 2 u to the third sine squared plus u to the third. We can do some simplifying. We can do some factoring of those first two terms. Left of the cosine squared times sine squared. So those first two terms just simplify down to a -2 u to the third. Plus u to the third, that's -1 u to the third. And so this is the integral we need to find. -u to the third, du dv. The u's go from 0 to 2. The v's go from 0 to 2 pi. I didn't show all my work for this because it's really similar to the integral I just did. But basically, you integrate the -u to the third, you get a -u to the fourth over 4. Plug in those bounds of integration, that becomes a -4. Integrate that with respect to v, plug in the bounds of integration, and there we go, exact same answer of -8 pi. All right, that I think was that was my last example in this long video. Please let me know if there's anything I can clear up.